On projects where people want to know what the one number is. Okay. And the one number, there's various one numbers, right? How much is it going to cost? When will it be done? And they always ask for that one number, right?
It's even better when they tell you what that one number is.
Yeah, well. So, I think we've all run into problems where we've been asked for that, or we've been forced into a situation where we have to give one number, and it feels kind of icky to do it. And so we try to hedge it, or we work out a range and then we give an average of what we think possible outcomes could be. And I don't know, but lately I've come to believe that the road to hell is paved with averages. And when we use averages to sort of project into the future, we're often wrong. It's weird that it works out that way. So I'm going to spend some time today talking about a future in which there are multiple possible outcomes. And I think that's a future that most of us sort of live with. The future is uncertain. A number of different things could happen. And the second we accept that there are multiple possible future outcomes, then we're living in a world of probability. And in the deterministic world, the world of the one number is no longer really reflecting reality. So that's what probabilistic forecasting is about, probabilistic planning. And so we'll dive into that. Now I want to do a couple of things before we get going. One is there will be an attendance sheet going around, and I'll ask you to sign your name. And we do that because of the support that we get from Communitech and the support we get from our sponsors. So we're fortunate enough to have Unitron sponsoring us. So they're providing food on a regular basis, and that's wonderful of them. Unitron is, for those of you who don't know it, is a local company that builds DSP-based products, mostly hearing aids, and there's a huge software component to the work that they do, and we're grateful for their support. The other has been asked if it's okay to videotape this, and I'm fine with it. If anybody has any objection to appearing on a camera, and you put these up on YouTube usually, yep. Right? So if anybody has any objection to being seen learning about probabilistic planning on YouTube, put up your hand, and we'll keep the camera facing this way.
Just object to being seen, doesn't matter.
Okay.
No.
Okay.
I'm okay.
So fair warning. And the last thing that I want to say is none of this is my work. This is all the work of a fantastic guy named Troy McGinnis. Troy McGinnis is a transplanted Australian, lives in Seattle. He's a statistician and works with teams to help them improve their performance, and especially their estimation and planning performance. And Troy is a wizard with reducing complicated statistical ideas to their simplest form. He's on a mission to get people to live in a probabilistic world. He's the most generous guy I know. With his work, all of his work is freely available. He maintains it in a public GitHub. I'll give you the link later. So all of this stuff that you see today, the spreadsheets, the worksheets, the presentations, all of it is freely available under Creative Commons license. And I happen to know Troy, and I've been in many of his sessions in various places. So I know that he's sincere when he says, please take this and use it. And just, call me when you need help. is his stance. And so thanks to Troy McGinnis. So let's get going. So here are the first reference. And Troy's company is called Focus Objective, and he actually sells some simulation software. But he makes these spreadsheet versions are freely available, as I mentioned. So how do you forecast? Do you use a tool like this? When somebody asks you what's going to happen, the magic 8-ball, turn it over and try to seek inspiration? Or maybe this is your tool of choice. Somebody asks you for estimates. And some people really like this tool. And sometimes when we're trying to piece together what the future might look like, this is about as good as it gets. Unless, of course, you've been to this session. So, as I said earlier, once we accept that there are multiple possible outcomes, then we're living in this probabilistic world. And the one number won't help us anymore. A really simple illustration of that is just your daily commute to work. So we all have this idea in our head that it takes us some number of minutes to get to work. But nobody, in my experience, can say it's exactly the same number of minutes every day. Sometimes,
Especially this summer.
sometimes there's quite a lot of variation between the smallest number and the big number. And so it's looking at that variation and understanding that variation and using it to your advantage to plan the future that becomes so important. So if one day it takes you 10 minutes to get to work, and another day it takes you 70 minutes to get to work,
You live in Waterloo.
you probably live in this area. But you need to take that into consideration if you need to be absolutely certainly somewhere for a meeting. When do you leave home is the question. And so it is with projects. If you have a fixed delivery date, the question is not when will it finish, but when do I need to start, given my experience of delivering packages. So at the root of this is some historical data. And historical data, just like our travel times, is a range. So teams have a range of delivery history, and there's some probabilities associated with that. So this is the one idea you need to carry away, if nothing else. If you have some data, use it to forecast. Forecast based on sparse or incomplete data is better than a forecast based on no data. If you don't have actual data, then absolutely use a range. And so if somebody asks you, how long does it take to do something, and you answer with a single number, that's a problem. So always answer with somewhere between here and here, because there's variation in almost everything that we do. And if you can't get a range estimate, if you're unwilling to provide a range estimate, then no kind of forecasting process is going to help you. So here's what we're going to do in the next hour. We're going to have a little refresher on statistics to undo all of the statistics that you remember from high school. How many people in the room are statisticians, first of all? Good. No. How many people in the room are mathematicians? Have a math degree or CS degree? Okay, and no statistics, right? Okay. So this is so common. I mean, I work at D2L. The place is filled with mathies, and you start talking statistics to them, and it's like the air went out of the room. It's like, we didn't do that stuff. So we'll have a little
Engineering
refresher.
required statistics when I was there.
So we'll have a little refresher, and then we'll debunk some myths. How many people think you need a lot of data to do reasonably accurate forecasting? Like big data. You need tons to get accurate, right? No? Okay. Anyway, we're going to test that. Just how much do we need? Then we're going to talk a little bit about getting data, and then we're going to show how this can come together with one of Troy's tools. And I hope that you'll leave inspired to explore some of this stuff. So here we go. So I have some exercises. I'd like you to work maybe in threes. And so if you could pass this stuff down and sort of group in threes. I'll go on that. I have some pens. People need anything to write with? Or do people have things to write with?
Does each person need one of these, or just each group?
Each group gets a sheet of paper.
Each group.
Are you participating or just taking pictures? Okay, then we'll
Yeah, shoot.
So you're at the center of a group, or you're
Yeah.
okay? So this is really to refresh your memories about what probability is. So probability, those dirty statisticians, they use these funny symbols like P equals probability, is the total number of right answers over the total of possible answers. So we're going to test this. How many possible values are there for six-sided standard dice? Anybody?
6.
Awesome!
We thought there was a question at first.
This is tricky stuff. Okay, 6. So question 2. How many values of a six-sided dice are less than 4?
3.
Okay. So question 3. What's the probability of rolling a value less than 4 on a standard six-sided die? 50%? How did you get that number? You said it out loud. Okay? So 50%, absolutely right. Number of right values divided by the total number. So what's the probability of rolling at least a 2?
5 over 6.
Okay. 5 over 6, you say? So what is that? Sort of 83%?
Roughly.
Okay. Awesome. I see a pattern here.
The only one that isn't.
So what's the probability of rolling a value less than 5?
That should be
67%.
It should be 60.
I hear 67%. Is that general consensus in the room? Plus or minus about a third of a percent. That's like 2 and 2 equals 5 for large values of 2.
It's 66.66.
Okay. Okay, I'll give you the repeating digit. 67%. Okay. So flip the page. Very difficult now. Troy's really testing you here. How many possible outcomes are there for rolling 2 fair six-sided dice? It's not a trick question, and there's a visual clue here.
possible outcomes.
36 possible outcomes. Awesome. So this has been battle tested, this particular test. You can tell because he's had to introduce the word fair.
There's 36.
And question 7, how many values, the sum of the two dice, are less than 6? Again, there's kind of a visual here. Anybody? Bueller? 10. Awesome. Okay, last question. This is the toughest one. What's the probability of rolling a combination of less than 6? 10 over 36. And that's all the statistical knowledge you need to know to conquer this session.
The answer's here. The answer's here.
Okay, any challenges for that? We're all good with how to calculate probability? Okay, so now we've undone all that statistics stuff, all the crazy stuff that you learned in school. And we're going to learn how much data we need to actually forecast some stuff. So finding data is really sampling data. So we're trying to pick examples of data that represent the probabilities in our world. So back to the driving, we would sample all of the durations of time we spent driving, and we would pick, this day and that day and that day. And that helps us determine the range. And we want to do that with as quickly as possible and with the least data possible. So, and we do this by, so that we don't need to collect all of the data. We don't need to have all of the story counts and all of the story sizes if we're working on our projects. But if we only take a sample, we want to be sure that we're confident that there's not some big secret cache of data that's outside of our sample. So here's an example of statisticians at work. This is a true story. It comes from World War II. And the Allied forces were really concerned with the number of German tanks that were roaming across Europe. And so they had all kinds of sources of data and sightings and spy networks. And, so military intelligence made these 3 estimates of the number of Panzer tanks Germans had on the ground in Europe. In June of 1940 and 41 in middle of August, middle of summer in 42. So 3 years. These numbers feel like kind of accurate?
I think they turned out to be low.
You think these numbers are low? So some people thought, I don't know about these numbers, they're kind of weird. They could be high, they could be low, I don't know. But let's get some statisticians on the... And what do you think the statisticians came up with? Put up your hand if you think higher. Higher statisticians are going to be higher than these intelligence estimates. This is what the statisticians came up with. And how did they do that, you might say?
Yeah, those are wrong.
How many samples of German tanks do you think they needed in order to come up with these numbers? More than 10. Put up your hand if you think more than 10. Okay, less than 10. Couple. More than 50.
I don't know what you're referring to.
Okay, okay. We're trying to say how many samples of tanks do they need in order to come up with this number?
What's a sample of a tank?
An actual physical tank.
So they counted X many tanks in a space or a given
Yeah.
volume or area.
How many do you think they need in order to come up with these numbers? What kind of sample, well, I'm saying physical tank, what other kind of sample might come to mind?
How many battles, how many things they've seen in battles?
How many battles? So,
1 in 20?
okay, you're saying 20 tanks?
1 in 20. So if I have one specimen, I can multiply about 20 times and
Okay.
it'll give me an idea.
Okay, so just to jump ahead and kind of get to the punchline here, I'll come back to the sampling question. So when they actually counted the tanks after the war, these were the actual number of Panzer tanks that were in service at these points in time. So this was from German records. So this is military intelligence best guess. This is statisticians based on some sample we'll talk about in a second. And this is actual count. You think the statisticians are valuable? A lot closer. So this is their sample. 2 captured tanks. So they captured 2 tanks. Each one of those panzers had 8 axles. And each axle had 6 wheels. And so they had 48 wheels per tank, 96 wheels in all, and every wheel had a serial number. Because German engineers. So now they have 96 samples, and they got them this level of accuracy. It's an amazing story. So, how did they do that? So we have this range, actual minimum, the actual maximum. What's the probability that the next sample will be outside what you already know? So they get the highest number and the lowest number. What's the probability it's going to be in between? Anybody? It would be 50%. So we can do this calculation through all of these intervals, sampling intervals. And so we get the next one. Of course, there's some caveats here for this. Matthew's in the crowd. So no dupes. I'm going to throw the dupes out. And we're assuming a uniform distribution. But we can calculate for each sample what the probability is going to be that it's in between the range that we've already seen. So it's quite amazing. You actually start to converge quite quickly. That when you get to your 12th sample, almost 83% certainty is going to fall between the lowest and the highest number you've already seen. Because these probabilities at the edges keep getting smaller and smaller and smaller.
But they only had 2 samples.
They had 96.
Oh, they had 96 wheels, but,
So they're using the numbers on the wheels to see what the range
oh, I see what they're doing. Okay, yeah.
of serial numbers on the wheels is.
They're assuming that the wheels are numbered
Consecutively,
consecutively.
which would be reasonably, from a manufacturing facility, yeah, that'd be reasonable.
And they're also assuming that the wheels aren't put on tanks consecutively.
It'd be more valuable to see how
Okay.
big the serial number is, and that gives you an idea of how far they expect it to extend.
So, does anybody have any argument with this particular process? Like, does it seem reasonable? So we'll go through an exercise to actually make this real for you. If you want to pass these out. Pass them down. So one of the tricks to doing is actually not a trick. One of the challenges in doing sampling is to make sure that we actually get random samples. So we're going to use dice to do some random sampling. And we have we have these fancy two-sided dice that we're going to use for this exercise. Sorry, multi-sided, 12-sided dice. We'll put the other ones aside for the moment. And so if you roll a 0 on the single-digit one and a 0 on the double-digit one, count that as 100. So that this note here. So in groups, what I want you to do is to roll a random number using these dice, and just go down and record what you roll. So in the first column, what was this roll? And the next column, what the lowest so far is and the highest so far. And I'll give you, says you need 10 minutes, but you probably only need 5.
That's cool.
What is it?
38.
Okay, so we've got under 9 sections. One group, 2 groups, 3 groups, 4 groups. The difference, yeah. Okay. So how many rolls did it take you to get to the?
That should go to 15.
Yeah. So how many rolls did it take you to get to a bigger range? I mean to 80.
Oh, sorry.
So you're under 9. How many?
In 3 we got to 90.
3 rolls. 7. 2. 3.
When you got to 90, your low was under 10.
Yeah, we had 8 and 90.
Wow.
I think ours were 80.
Jason's still rolling.
We had 91 after 6.
Our highest was 89 and our lowest was 99.
So the lowest.
No, we were very bimodal. There was either really small numbers or really big numbers. There was hardly anything in the middle.
Okay, so this game down here, 10. You guys were 6, 7. So what this range represents is your sample space, lowest and highest. So you know that your number is somewhere in there. And for sort of 80% of all circumstances. So some people got there with as few as 2 samples and 3 samples. This is so the notion that you need tons and tons of data to get useful distribution patterns. I hope this can be debunked for you. Now you might be kind of suspicious with just 2 and want to roll some more, but this is really an exercise to sort of drive home the fact that sampling is a really, really powerful technique, and you don't need lots and lots of data. Does that make sense to people? Yay, sampling. So how do we get historical data? And then how do we use that to get actual estimates? So Troy, as I mentioned earlier, is a bit of an Excel maniac, I guess is probably a good word. Anyway, he does lots of Excel work, and he was at home ill one day. Now, if I was at home ill, I would be reading a book or sleeping, but when Troy is at home ill, he's using Excel. And the challenge he posed to himself was, how many charts, illustrative charts, can I create
In a single day.
if I just know the story type and the ending date? It's the only data I have. I have a story of a particular type, and I have the date that we finished. And then, so he built a number of charts in his Excel spreadsheet with just that data. And then he thought he'd really challenge himself and say, well, what if I knew the start date too? How many charts could I build with that sample? So he's imagined that he's got a bunch of user stories, and he knows what day they started and what day they ended. How many charts do you think he built? Too many? 7? I did 7. Anybody else? Seems like a lot of charts. Then he got to 17 before he stopped. And these are all different representations of just that data. And some of them are familiar, and we'll go through these in a little bit. So here's a standard scatter plot. Right. These are, the durations of the days. Some of us are familiar with cumulative flow diagrams, which are pretty standard. Here's my favorite one. This is incredibly useful chart because it shows how many stories started and how many stories completed. And you can start to see the pattern of this team as it picks up work and then actually completes work. So 17 charts so far. Throughput, planned and unplanned, throughput histogram, cycle time, planned and unplanned. Fix that for you. Cycle time histograms, work in process, cumulative flow, arrival and departure rates, unplanned work percentage, because remember he indicated what kind of work it was, whether it was planned or unplanned, a story or whatever.
Defect.
So these are his types, story or defect. So there are 3 pieces of data. What kind of story it is, when did we start it, and when did we finish it? So this is kind of interesting stuff. Most of us sort of have a hard time telling the story of how our team has been performing. And this is really all we need to tell a great story, or at least illustrate maybe that we don't have a great story to tell. So this is, I can show you this spreadsheet and show the charts a little bit bigger, but I would urge you to go and just download it and play with it and put your own data in it. Because that's what I do with our teams. Like, go put your data in here, and then let's have a conversation about how you're performing. See if I can bring up. So this is kind of stage 1. It's the simplest representation of actual data that he has. So then he thought, well, how can I take this a step further? How can I create a tool that would allow people to start to play with either live data if they have, or if you don't have data, what do we use?
Ranges.
Ranges. Yay. So that's what he did. He went and created a forecasting tool. And we'll get to it in a second. But I just want to go over some more detailed statistical jargon for you. And so we use this word mean. Anybody know what? Familiar with this word? Okay. So this is a fantastic site, Math with Bad Drawings, that helps you try to understand these things. So here's this poor candidate going, how much are you going to pay me? And the hiring manager says, well, you know, the average starting salary around here is 80 grand. I go, yes, I'm in. And
Yeah.
there's the reality. So now you maybe understand the mean is also called the average to us laymen. And maybe earlier I said the road to hell is paved with averages. Here's one instance of it.
In this case, the median would have been a much more interesting number.
That's right. So median, anybody familiar with median? So we'll use these numbers. The mean or the average is the mathematical center. The median is the point at which half the values are higher and half the values are lower. So here we have median. So this is a very common circumstance in our world. Why should I invest with you? Well, I don't want to brag, but my friend has a median gain of 8% a year. You go like, wow, I'm going to give you my money. No. So when people start throwing around terms like mean and median, maybe it would be better to look at the distribution, the shape of the distribution. So here's the fundamental problem. On average or median, arithmetic fails. Just doesn't serve us well. So try to add ranges arithmetically, and it doesn't help us out very much. So in the probabilistic world, the future is not a single point. The one number doesn't rule. The future is a shape. And it's the shape of this distribution that we encounter. And some are more likely than others. So this is kind of where it's typically the strongest memory of statistics is this bell-shaped curve, also called a Gaussian distribution or a normal distribution. And everybody is familiar with this? Yes, I see nodding heads. So this is great. In the normal distribution, the mean and the median happen to be the same. And the mode, which is the most frequently occurring value, all happen to be the same. And that's great. And easy to remember, and easy to calculate variance from that, either side. But there's this really sad fact, and that is our world is not normal. There's a fantastic book called The Flaw of Averages that can help you explore this if you want to dive deep. Not my preferred evening reading, but it's written in quite an amusing way. So if you want to explore why averages are so problematic, that's a great place to go. So when somebody asks us, what's the one number, and you're going, oh my God, it could be any of these things, it could be from here to there, I'll just give you the average, then we're selling ourselves short because there's 50% probability that it's going to take longer. That doesn't seem like a very good bet to me. So what we really want to do is get this number out here, say, like an 85% bet feels a little bit better. If somebody needs something with absolute certainty, then you need to go out even further. So in a normal distribution, that's bad enough, but in the kind of distribution that we tend to see, it's even worse. And automating the problem doesn't help because of the arithmetic problem. So Troy's challenge was, can I bend Excel to my will in order to solve this problem? And there are techniques to do that, but he made it even harder for himself. No add-ins,
And no macros, that's great.
no macros. So, so it truly is bending to his will. And he created a number of forecasting sheets. So that he has a forecasting sheet for a single story, and then he has a very useful one called a multi-cut forecasting sheet. Again, all available on his GitHub repo. And I'm going to show you what that looks like. But here's the input fields for his forecasting spreadsheet. So you need a start date. And then you can see what happens here is, what's the low guess of how many stories I need to complete, and what's the high? And then he recognizes that, we learn as we go along. And what looks like one story turns out to be 3 as we split it or we add on to it. So he has this factor for split rate. How big will that pool of stories grow? And if it's not going to grow, like we're awesome story writers, then you leave it at 1. But if you're not too sure, or your team's experiences, we turn over rocks and discover more stories, then you might want to put this up at a 2 or 3, so multiplier. And then how much work do we get done in a particular period of time? What's the historical performance of the team in stories? You can do it per week, or you can do it per sprint. You could also use this spreadsheet not with stories, but with story points, if you prefer. I don't know why you would, but that's a sort of, some teams do that. And you can put your actual data in, if you have data, throughput data for your team, or you can put ranges. So in this particular case, he's saying, I estimate that the team does between 1 and 5 stories per week. So this is all very cool. We're obeying his strong recommendation to use ranges instead of points. What does he do with this? The back end of the spreadsheet, he runs a calculation 1,000 times. And every time it runs a calculation, it picks a value in each of those ranges randomly. So if we were to do this by hand on our desk, we would never get it done. But we have these things called computers, and they can compute for us. So this technique, so for every set of random data, it calculates, when will I get done? And then it goes, oh, let's do it again, let's do it again, let's do it again. And we build up this distribution pattern. What might the future look like? And this is a very typical pattern for knowledge work. So skewed left, long tail right.
It's also the distribution pattern for machinery breaking down.
Yeah.
I had to go through it.
So in its purest form, it's called a log normal distribution. If you want to get really technical and fit it, there are many curves that it can fit to. What's popular in the Agile world right now is a distribution pattern called Weeble. But I don't want to dig into that too much. You just need to recognize the shape. That there are very few stories for software development teams that get done in a day, and then there are these horrible ones out here that take forever and ever and ever and ever. So, where is the average and where is the mean in this? Or where's the mean and where's the mode? And how does that help us? Well, the mode is over here. It's the most frequent occurrence of how long it takes us to do a story. And it's actually to the left of the mean, which will be around there someplace. And our 85th percentile kind of represents an acceptable level of certainty. It's going to be out here someplace. So what happens when you go to a team and say, how long will it take you to do this story? What do they say? Apart from, I don't know.
Depends.
Well, what normally happens is the last time we did something like that, it took like 4 days. And what are you tapping into when you do that? The mode. This is what I remember. Most often, a story has taken us this kind of, so I say 4 days. And guess what happens? My forecast completely ignores that experience that you know is going to guarantee that it takes longer. Anyway, the Monte Carlo process allows us to make these calculations multiple times, in this case 1,000 times. There are Monte Carlo simulation tools out there that can do 5,000 times. And it creates this simulated burn down chart for each one of those sets of samples and builds this distribution. So this is pretty cool. Now we have this distribution. I can go back and I can calculate how likely is it that I'm going to finish the stories that I've defined. So you have a list of stories, you have a range for each of those stories, and Troy's spreadsheet says, yep, almost certain that you're going to get this one done, and this one done, this one done, this one done. This one's a little iffy. So I'm inside my, or I'm outside my 85%. And these guys down here, no chance.
Well, he's predicting how long the project's going to take.
Yeah, so the assumption here is that you work on these stories sequentially. So you need to bear that in mind. But
Right.
now for the first time you have you can tell a story about the future. It's based on realistic ranges and is using our friend Monte Carlo and probability, very simple probability tools to say, here's the picture of the future. I guarantee if you use this tool, you're going to cause product owners heartburn. But because for the first time, you'll be able to say, here's some data and here's some mathematical rigor applied to that data that gives you a view of the future with a probability associated with it. And if you don't like that, then you need to either change the data or shift how certain you want to be about the future. This is just like gold. Stunned silence, quiet appreciation. What am I? I'm trying to get a sense of.
Yeah.
So I can show you what that actual spreadsheet looks like, if that would be helpful, or we can dive into another exercise before we get going. Spreadsheet, exercise, spreadsheet. So this spreadsheet is the actual charts that he was showing. I'll just run through these very quickly. So based on this data, so it's just completed date, start date, and what kind of story it was. I don't know how much data is put in there. 142 stories. You can generate these charts. So this one is showing how many calendar days. So it's just the history of things that have been completed and a trend line. So this team's improving, completing more stories, but it's got some peaks and valleys, which is to be expected. There's just a throughput histogram. Again, I'm not sure, they had one story that got done in a day. And you see that same kind of pattern skewed left. Planned and unplanned. This requires defining defect work as unplanned, but It allows you to do that in these settings here. So planned work type is a story, unplanned is a defect. You can change the labels if you want. And over here, what percentage that unplanned is of your total work. So if you have a team that's going wild, pumping out features, and the testers are going crazy because nothing's working, this is a really good chart to sort of hone in on that conversation. Here's what's this one? Calendar days to complete an item, so that's just simple subtraction, but you can see how it's changing over time. So people, if you're struggling with big stories, that's a great chart. You start to, or if there's lots of variation, which is kind of indicative of an immature team or a new team, that they can't quite size their work in a consistent way. You get big variation. That would come up in this kind of chart. Completed item cycle time and calendar days. Again, that shows you how this particular, I think it gets very tricky. You put the percentile marker in here, so he wants to see the 95 percentile. So you can see which stories are outliers, like how accurate or consistent are we being. Number of WIP items per week, items in process, throughput, and average cycle time, all in a single chart. And then this one's really kind of interesting. Weekly trend of progress, throughput, and cycle time. So we're seeing here is the throughput going up and down. The blue, the average cycle time is the green. The blue is the throughput, and this is the average amount of WIP that the team or this data set is representing. And cumulative flow diagram is very standard. So the orange area in the back is all of the WIP, so your total backlog, and the blue is how much has been completed on a date-by-date basis. Here we have started versus completed, number of items per week. So this can help you have a conversation with a team that likes to start all the things and not get done any of the things. And this is the same kind of data netted out. So in this particular week, they started more things than they finished. And oh look, they did it again. And now they've got more things finished than they started. That's a good thing. But then they went crazy. And they finished some stuff, they started some. So we want to see that even out a little bit. And if you saw like nothing but red for weeks on end, you go like, why are you guys starting more things? Because nothing's getting done. So I love this chart. Anyway, 17 charts, 3 pieces of data, free for the taking, thanks to Troy. I strongly urge you to do that. So this particular sheet is called Troy McGinnis's metric spreadsheet. Let's see if I can find multiple feature. What's this one? So here you can see, here comes with instructions. You can get full instructions on what goes where, what it is. And here you can see, here's the input screen that I showed you before. He also makes adjustments for month by month. So here, for example, in December, we know that the productivity of the teams is going to be probably half of what it normally is because of holidays and getting ready for holidays and recovering from holidays. So if you have a sense of availability of your team, you can reflect it here. If you choose, I've chosen estimates here, but if you choose to actually put throughput data, there's another sheet that allows you to enter your own data. So here's you can see what's happened here. So I have a split rate of somewhere between 1 and 3. And I have a start date and a target date. I love that word target instead of end date. And then I want to see, I'm willing to roll a 50-50 bet. So, I'm satisfied if there's a 50% likelihood of the story finishing. But I could change that. Change that to E5. And you can see that will affect the actual forecasted completion date. So I have a bunch of features here, 7 features. I have a range of how many stories are likely associated with those features. And it goes off and does its Monte Carlo magic in the background and comes out and says, yeah, you can get the first 3 done and by your target date, and the rest are highly unlikely.
I have a question.
Yeah.
So in an agile environment, there is the learning curve that the team gets with each sprint, yeah?
Yes.
So how that is factored in here when you do estimate? You cannot factor in the learning, yeah?
Well, actually you can over time. There are a couple of different techniques. So one is to just slice off the front end and not pay attention to it. And say, look, once the team gets into flow, then at what rate do I need to complete work in order to get to where I achieve? Because most projects follow a pretty standard pattern of an S-curve. So not much happens in the first sort of 20% of time. As environments get set up, people learn the domain, team gets sort of gelled, and then all of a sudden there starts to be a steeper slope of productivity, and then towards the end things taper off, and we're more polishing and not actually creating new features. So that's quite a standard pattern. You can accommodate that with planning in chunks, if you like, across the S-curve. So there we go. This is what you can do with probabilistic planning. Just very little data, but an understanding of the future as a shape, and how can we generate that shape and use Monte Carlo testing to do that. This is not the only tool to do this, and I've actually done this with teams. There's a statistical package called R. So I had a team that was doing more help desk type work. So the shape of their curve was different. It was skewed even further left, because a lot of the things that they did within one day. So that was, you can imagine the curve kinds of looks logarithmic. And they had very few things that sort of took longer than 2 weeks to get sorted out. But so I had 400 tickets. I could extract the data from Jira. We extracted that data. They used R because they had a mathy on their team who wanted to go and play. Built a representation of that data, and then they used it to sort of schedule their time or make commitments, better promises to people, because they truly understood how long it would take to get something done. They knew the backlog, they knew their performance. Somebody came to them, I said, I need this urgently. What's urgent? Well, I need it, within the next 2 days. 40% chance of that happening.
I have another question. From your experience, if we are in the scenario from feature 4 down, yeah? Those are highly unpredictable, making a reasonable estimate.
It's unlikely, yes.
So then how you report that to the management regarding how long or how much? Or
Yeah, well, here's the forecasted completion date. I don't like that. What can we do about that? So now we can reorder the feature. Oh, that's your pet feature? We'll just move it up the stack. So the problem is not when will it get done, it's when do we start?
Yeah.
Right.
The iron triangle kicks in now,
Oh,
and
absolutely.
you decide what's more important, the day you deliver or how much you deliver.
But until you have this kind of,
It always comes down to that.
Until you have this kind of support for your argument, then everything is equally possible, right? And you go like, I want all the things.
We had that conversation with a customer once, it's like, it's gonna take weeks to do this, and we did do this one, which would you like first? And she says, I want both of them.
Yep.
2 weeks is what we told her. And if you want one in a week, make a decision. You know, it's,
Yeah.
So there are slightly different takes on this. I don't know if any of you know Jason in the room in the back. Jason and I worked together at a government agency, and Jason actually had a team that was challenged by growing backlog, and it wasn't visible. So we made it visible. So the team throughput was pretty steady slope. So let's call that X. And but the backlog was growing at like 3x. It wasn't until we actually plotted that and made a projection of it and took it to the SVP and said, look how these things are diverging, and your end date is 6 months out here, and there's going to be this gap. Do you think you're going to be a happy guy? And they're like, hell no. And then the question is like, why is this happening, and what can we do about it? It's not, whip the troops harder. But that's generally the response, right? Oh, make them work weekends, make them work overtime. But
Make them quit and go to somewhere else.
well, that's often the outcome. But until you have some data that can paint a picture of the future, in this case, it wasn't even probabilistic; it was just straight line. But it's a bit of a problem. So I want to just hop back over here. We're just about done. So we got 5 minutes to go. I'll leave you the Monte Carlo simulation. It's a similar exercise. You can do a short Monte Carlo simulation by hand just to convince yourself that, yeah, this actually works. But it's not really completely necessary to do that. So Troy's actually filled out the last 11 files, so you just need to do the first 3. It's just a sheet I have. No, I haven't even got the right sheet, so that's good. Sorry about that. But it's the same idea. You take some random samples. Here's this random number generator, again using dice, and we roll. We can count the likelihood of getting some stories done. If anybody wants this information, you can just send me a message and make sure you get the correct sheet. This is another view of the spreadsheet that I showed you. So just a little glimpse into what's happening at D12. So I distribute this sheet, make it freely available to all of our dev managers and engineering directors. But I also make their data available. So we have a Rally shop with lots of data. We actually extract the data on a daily basis and manipulate it in our BI tool, which happens to be Tableau. So I can pull up any iteration or all of them. I can look back in time over any particular period, and I can look at the state of the work that I'm interested in. So this shows the number of days that it takes us to get a user story done for all iterations in the last 3 months and have a state of accepted or ready for release. And picture's not bad, but it's not great either. Because I'm looking at anything that is past this line, it crosses as an iteration boundary for us. So we run in 2-week iterations. So the story takes longer than 10 days. Then we've got teams that are flowing over from iteration to iteration. It's not necessarily a bad thing because our release boundaries are 2 iterations. So we do have some stories that can flow across, but it's not preferred. And then we get some outliers like this. It's a story that took a month to do. So often when you look at this data, you need to understand from a coaching point of view or an improvement point of view, you may want to chop off the outliers once you identify them and sort of tell their story. This particular data shows bimodal stuff. So you really need to be careful about what kind of work is being captured here. If you see a bimodal distribution like that, it's usually there's 2 different kinds of work. So if you can identify the other kind of work, maybe defect work takes a shorter period of time than net new feature work, separate that out somehow, and you'll get a truer representation. But still, this data is better than no data. I'm a huge fan of CID charts. This is a particular large initiative that we call Daylight. And it's gathering data from many, many different sets of activities. It was a little bit hard to piece together, but it's great for us to have a conversation with the sponsor and the executives to say, you declared this thing was back here and nobody knew what it was. The gray represents everything we've learned as we go along. It needs to be done. And the green stuff is the stuff we've actually completed. So you can see the gap. So now there's conversations about what are you doing and what have you done are relatively easy. Because if this is all gray, the skinny little green line down here, that would be a different conversation. But the team generally has been keeping pace, except for this, oops, we uncovered a huge, big bunch of work here. We look crazy. Here we actually killed some stuff. Oops, found a bunch more stuff. But with one single sort of graphic representation, now we can have this much better view of the world. This is our nirvana. This is where we want to get to. This is the work of Larry Maccheroni, formerly of Raleigh and now independent, or I forget which company he's working for, relatively independent statistical technical coach. But we want to be able to look back at how the team has been performing at a particular point in time, see what our backlog is. We'll make the simplifying assumption that what we know we need to do is all that we need to do, which is not necessarily true, but generate, using Monte Carlo techniques or some other predictive analytic technique, generate a shape of the future, and then we can have conversations about where is that likely to fall in terms of completion. And so we're going to do that for, just like we did the historical data, we're going to lay this on top. And so anybody will be able to go and self-serve review the future for the team that's working for it. If you don't like the data, go change the underlying sentences. can see if you just do that straight line, and we do this all the time, right? Okay, we're here, and we project out with a straight line estimation, we don't even hit the mean. So if we do linear extrapolation, chances are awesomely good that you will be dramatically wrong. So each one of these lines represents a path in the Monte Carlo simulation. Distribution is total, and then we can go, okay, you want to make a 50-50 bet? We'll be done at this iteration. You want to make it to be absolutely certain? Trade show, you have a big public product release. Don't start making promises before we're sort of out here. If you've made the promise here, then we need to talk about how we can shift all this left. Do we augment the team so we get more capacity, reduce the scope, all of those traditional project management discussions kick in. But without this view of the future, anybody's opinion is fair game. That's all I got. 6 o'clock on the nose. I hope this has been interesting. I'll post the links in the meetup group. And thank you for listening so patiently to me. But more importantly, thank Troy, because he's made all of this incredibly useful stuff so freely available. And if you use it, tweet it, and let them know. And if you want to dig in deep inside your organization, I'm sure you'd appreciate a call with focus and objectives. Here we go. Thanks.
Thank you.